Everyone, I am Arpan Jain and I welcome all of you to the another exciting paper session of HOTI 2023 conference. So this session is on SmartNICs and we have two exciting papers related to NVIDIA's data processing unit, commonly known as DPUs here. So let's welcome Yuke, the presenter of our first paper in this session titled Characterizing Lossy and Lossless Compression on Emerging BlueField DPU Architecture. So Yuke is a PhD student in Patsy's lab of Computer Science Department at University of California, Merced. Her research interests include high performance computing, MPI, RDMA, and DPU. With this, I hand over stage to you, Yuke. So please share your slides and let's get the presentation started.
Okay, thank you, Arpan. Okay, hello, everyone. This is Yuke, and today I will present our paper characterizing lossy and lossless compression on emerging BlueField DPU architectures. Okay, so this is the outline for my today's presentation. Firstly, I will briefly introduce our motivation and some background according to the compression techniques and of course the DPU. And then second, I will introduce our methodology for the characterization. And then I will show some performance result. And based on that result, I will give some observations and summarize them as a takeaway. And finally, I will give some discussions based on our observations of the performance characterization result and also make conclusion. So let's start. So today we as you know, like we live in an era where the big data, high performance computing, and machine learning technologies are converged. So all these workloads, they will need and produce, generate, and transfer large volumes of data. So this data, when combined with the computational power of the HPC and also the analytical capabilities of the machine learning, they can lead to groundbreaking discoveries and innovations. So therefore, the data plays a significant role in these technologies. However, with these vast volumes of data generated for storage, processing, and communication. For example, there will be more file spaces are needed for storage in this data. And also the communication latency will also increase rapidly with the increase of the message size. So this has led to the data volumes in communication and storage becoming a significant performance burden. So especially for applications that aim to perform efficient analysis and derive meaningful insights. So there arises a significant challenge. How do we efficiently store and transmit this data? So this is where the importance of the data compression comes into play. Data compression is a widely adopted solution to address these challenges by encoding data to reduce its original size, and compression can help in storage and transmission. So there are many applications from machine learning to the database and the network communication. They all utilize the compression techniques to enhance performance. So the data compression not only reduces the storage requirement, but also speed up the data transmission, which makes it a crucial component in the modern applications. So there are two primary techniques for data size reduction or data compression. So the first is the lossless compression. The lossless compression, it can reproduce the original data during the decompression operations. Generally, it achieves lower compression ratio compared with the Lossy compression. But it is important in the scenario where the data integrity is the first priority. So there are several state-of-the-art lossless compressors, and they are actively used in the various applications. For example, the deflate compression and LZ4, Z-lib, and the Z-standard. So the second compression technology is Lossy compression. And the Lossy compression, it can achieve much higher compression ratio by sacrificing some data error. But it is essential because the Lossy compression offers a balance between data quality and compression ratios. Lossy compression is widely used in the scientific data compression area. So there are some widely used Lossy compression algorithms. First is error-bounded Lossy compression, like the SZ3 compression, and also a fixed rate Lossy compression, which is a ZFP. So let's briefly introduce the DPU, or data processing unit. So the DPU is a kind of SmartNIC which equipped on the host. And the DPU has the one general network interface card, or NIC, we call it in short, plus some system on chip cores, or the SoC cores, we call it in short. So for this SoC cores, it can run its own operating system, which means the users can program the SmartNIC, can program the DPU, and run some specific or isolated programs on the DPU. So this figure is an overview of the architecture of the NVIDIA BlueField DPU. So there are two series widely used in the NVIDIA BlueField DPU family, which is a BlueField 2 and BlueField 3. So both of them equipped with one general NIC, which is a Connect X series NIC, and also with 8 or 16 ARM cores. And that SoC cores can run its own operating system. And in addition, the BlueField also provides some specific hardware accelerators, which can provide much better performance on some specific tasks or operations compared with running them on the general SoC cores. For example, the BlueField provides the compression engine as a kind of hardware accelerators. So there are tons of works that have been done on the CPU-based data compression. And also the GPU-based data compression is also a really hot topic recently. But for the DPU-based solution, especially for these commercial DPUs, they are not well studied. So the DPU is a recent innovation that adds some computing power to a regular network interface card in the data center and HPC systems. So with that extra computing unit, the DPU is ideal for offloading tasks from the host CPU. There are several major network vendors have released their programmable NICs with varying architectures. And these DPUs not only offload tasks, but also provide hardware-based accelerators to enhance the compression and decompression performance. So leveraging DPUs with its capabilities can lead to resource saving and reduce the communication payload and accelerate the applications. So this observation motivated us, our research, to explore the performance characteristics of the DPU-based compression schemes and identify potential avenues for the future research. Then I will introduce our methodology to characterize the BlueField DPU's performance. So in one word, we choose 3 compression algorithms and running them on the BlueField SoC cores and the compression engine with 7 real-world datasets. So I will introduce them one by one. So for the compression algorithms, we choose deflate and zlib as the lossless compression, and we choose SA3 as the lossy compression. For the hardware platform, so what is the, I saw there are chat, okay. Can I keep the presentation? Sorry, backstage. Okay.
No, we can hear you. It's fine.
Okay. Yeah. Okay. Sure. Then I can keep presentation. So for the hardware platforms, there are we use both the SoC cores and the compression engine. And for the compression engine, we run the deflate lossless compression algorithms. And for the real-world dataset, we choose several datasets from different area, for example, from the observational data, parallel messages, and numeric simulations. And this is overview of this figure is an overview of our methodology. So we load the data into the BlueField DPU and calculate their performance based on our 3-dimensional way. And we record the corresponding characterization metrics, which we categorize them into 2 classes. The first is hardware utilization, which is corresponding to the CPU utilization. And the second is compression designs performance, which is compression and decompression latency, throughput, and compression ratio. So the cost, because we focused on the compression and decompression performance, so the cost of reading and writing data to the files are not included. Let me briefly describe our test bed. So our experiment based on 2 test bed. The first is our local test bed, which equipped with NVIDIA BlueField 2 and Ubuntu Linux, and with the Docker version 1.5. And at the end of the performance characterization result, we gave us a brief comparison between the BlueField 2 and BlueField 3. So that experiment running on the Thor partition on the HPC AC cluster. So Thor equipped with the both BlueField 2 and BlueField 3 with Rocky Linux and the Docker version 2.0. So moving forward, let's dive into the core of our research, the compression performance characterization of the NVIDIA's BlueField 2 and 3 DPU. So a critical aspect of our study is understanding the CPU utilization on the SoC cores of the BlueField. So given the limited power of these cores, especially when handling some resource-intensive tasks, there are a potential advantage in offloading these tasks to the dedicated compression engine, which is equipped hardware accelerator. So this figure shows the CPU utilization results for our 4 compression designs across 7 datasets. Within each design, there are 7 bars with different colors, which are the data sets with the size increasing from small to large, from left to right. So here have a few key observations based on this performance result. The first is lossless compression on the SoC core. It consumes more than 80% of CPU utilization. And second is a lossy compression, almost near fully utilize the CPU. And third is when compression engine is utilized, CPU utilization drops, but still has like 18% to the 53% with the data size range from the 9 megabyte to the 108 megabyte. So our first major takeaway is that even when the bulk of the compression processing is offloaded to the compression engine, the SoC core remains actively engaged. For a data size of 128 megabyte, the CPU utilization can still reach up to 53%. This is attributed to the core's involvement in tasks like data movement and memory management for the compression engine, and we will describe them in detail in the later slides. Then we have the performance result of the compression and decompression latency. Here is two figures for the compression latency and decompression latency on both the SoC cores and the compression engine with different compression algorithms. So the first observation is utilizing compression engine for the compression, it can achieve up to 26 times speed up with the largest data set, the 128 megabyte data set. And it can still achieve 3 times speed up with the smallest data set, the 9 megabyte data set. But the second observation is, but for the compression engine for decompression operations, it doesn't show much benefit. And even it shows the performance degradation up to 3.5 times on the small data set, which the data set size smaller than the 30 megabytes. So this comes to our second takeaway. The compression engine is up to 26 times faster than the SoC core for the compression operation. However, its overhead affects the decompression performance, making the compression engine less efficient for the dataset smaller than the 16 megabyte. So as we can see, we observe the performance degradation for the decompression operations when we utilize the compression engine. So we start to thinking about where the bottleneck comes. So in this slide, I will introduce the performance bottlenecks for using the compression engine. First, let's see the figure 1. This is an overview of utilizing the compression engine. So the process is, first we need to initialize the Docker environment and the compression environment. And second, we need to prepare and register some specific data buffer, which can be used for the compression engine. And then third, we should submit, we should wrap the compression workload as a job and submit to the compression engine. And then the compression engine will do the data compressing or decompressing and back to the compressed or decompressed data to another pre-registered data buffer. So the figure in the above is the time breakdown of this process. So we can observe the environment initialization and buffer preparation. It consumes 90% of the total compression time. So which is not ideal for us. And also the figure in the left corner, the x-axis is the number of jobs we submit to the compression engine at one time. And the y-axis is the total completion time of these jobs. So we also observed the limited scalability of the job concurrency on the compression engine. And also the compression engine has the maximum data buffer limitation, which is 128 megabyte for one job. So based on these bottlenecks, we should consider the further optimizations when utilizing the compression engine on the BlueField. For example, reuse the Docker-specific buffer and carefully select the appropriate job concurrency. So in summary, as a takeaway, using the compression engine, data staging and Docker initialization account for the 90% of the total compression time. When using the engine, consider further optimizations and the data size limit per job. Sorry, by the way, the Docker is SDK provided by NVIDIA. It have some drivers and APIs, and via that APIs, we can use the compression engine on the BlueField DPU. So then we show the compression and decompression throughput and the compression ratio. So here are some observations based on the result. First is the Lossy compression achieves much higher compression ratio. Of course, it's due to the algorithm nature of the Lossy compression. And then utilizing the engine with the lossless compression can achieve up to 25 times higher throughput compared with using the SOC core. And the third is decompression doesn't show much benefit due to the overhead when using the engine. So I summarize as a takeaway, utilizing the compression engine efficiently can achieve higher throughput on lossless compression, although it is a lower compression ratio. And finally, we give a brief performance comparison between the BlueField 2 and BlueField 3. And BlueField 3 is the latest released BlueField DPU at the beginning of this year. So the figures show the pure compression and decompression operations time on the SOC core and decompression engine, which means we didn't record the, for example, the initialization time consumption and the data preparation time consumption. So the figure A is a compression time comparison between the BlueField 2 and 3 with a deflate lossless compression on the SOC core. And the second figure is a decompression time comparison between the BlueField 2 and 3 on the compression engine. Also use the same deflate lossless compression algorithm. So we can observe the SOC core on the BlueField 3 can perform better than the BlueField 2 up to the 25%. And also the compression engine on the BlueField 3 can be better than the BlueField 2 up to 58%. So as summary in the takeaway, BlueField 3's compression engine shows up to 58% improvement over the BlueField 2, and SOC core shows up to 25% improvement, underscoring the BlueField 3's enhanced performance. And then I will give some discussions based on our observations for the characterization result. First is the compression engine is highly effective in reducing CPU utilization and outperforms SOC cores in most cases. And then the compression engine can outperforms SOC core in most compression operations. And using the compression engine is not straightforward, and further optimization on the utilization of the engine should be considered. And also, we in the discussion, we also gave several optimization tips for using the engine. So due to the time limit, the details can be found in our paper. So finally, let me conclude our work. We conducted a comprehensive performance study on NVIDIA BlueField DPUs and dive deep into its compression engine, comparing BlueField 2 and BlueField 3, and providing some key insights and design tips for the researchers. And the BlueField DPU compression engine provide up to 26 times speed up over the SOC cores for compression, but its overhead can hinder decompression performance. Thus, developers must understand its bottlenecks to fully utilize the compression engine. So we also have some further work. ongoing. For example, we are trying to deploy the compression design into some real world storage or communication applications. That's all of my presentation. Thank you, and please feel free to ask questions.
Okay, thank you so much, you, for the great presentation. I would encourage attendees to ask questions on the Slack. Yuke will be available even after the session to answer those questions. So I have a question on this, Yuke. So you mentioned that you will be working on the communication side. So there is an implementation by MRPitch 2, which uses the compression to optimize the performance. So have you considered that? And how will you, like in your presentation, there is a one figure where you show that with the number of jobs, the scalability is not great. So you cannot run multiple jobs. So have you considered running the compression on the BlueField compression engine and running decompression simultaneously on the SOCs? As from the figure, I see that SOC can have better performance for the decompression.
Yes, definitely. The material processing method is a potential avenue for the future research. And maybe in the future, we can try the MV-pitch decompression on the BlueField SOC cores.
Okay, and you mentioned that for the BlueField 3, you see that the decompression engine gives better, so like the compression engine gives better performance for the decompression, right? So
Yes.
So it gives a better performance than the SOCs available on the BlueField 3, or it is with respect to the BlueField 2?
Sorry, can you repeat the question again?
Yes, sure. So the question is the decompression on BlueField 2, does it perform better than the SOC or
if you refer to the whole processing unit, the whole decompression process, the answer is it should depend on the data size, and sometimes the decompression on the compression engine on the BlueField 2 is not as good as on the SOC core. But if we see the pure data processing which is a pure decompression operations on the compression engine, the answer is yes. The compression engine is always better than the SOC core, but you must try to optimize your applications like on the initialization and the buffer preparation. This part, yeah.
Okay. Thank you so much for the awesome presentation. And the audience can ask questions on the Slack, so she can answer it directly on the Slack. Okay, thank you so much, Luke. Let's move to the next presentation.
Thank you.
So next we have Ben Michalowicz presenting his paper titled Battle of BlueFields, an in-depth comparison of the BlueField 2 and BlueField 3 SmartNICs. So Ben is a third-year PhD student at the Ohio State University, working under Professor D.K. Panda and Professor Harish Subramoni. His research interests include parallel computing, heterogeneous computing, and as well as SmartNICs. So we have Ben here. He has pre-recorded his presentation, so he will be available to answer all your questions on the Slack. And after the presentation, he can answer those questions live here also. So let me share my screen.
Hi, everyone. My name is Ben Michalowicz. I'm a PhD student at the Network-Based Computing Lab at the Ohio State University. I'll be presenting my talk entitled Battle of the BlueFields, an in-depth comparison of the BlueField 2 and BlueField 3 SmartNICs. This paper was published as part of a larger project with Steve Poole at Los Alamos National Lab, and so I'd like to thank him, LANL, and the U.S. Department of Energy for their funding and support. So here's a brief outline of my paper.
Recording in
I'll start with
progress.
introduction, motivation, and problem statement, breakdown of the BlueField 2 and BlueField 3 SmartNICs, our experimental setup and methodology, followed by 7 experiments across 5 different subsets, and then I'll wrap up with my concluding thoughts, discussion, future work, and some acknowledgements. So for starters, we have 4 main drivers of modern HPC cluster architecture. We have our multi-mini core CPU processors, such as those from Intel, AMD, and ARM. We have our accelerators, such as GPUs, and more recently FPGAs, and even more recently the Grace superchip and its Hopper equivalent. Then we have our increasing capacity and clock speed of various storage devices, such as our SSDs, RAM, etc. And then last but certainly not least, we have the increasing capabilities and intelligence of our network cards, SmartNICs, and in some cases they may differ, our data processing units. For NVIDIA's BlueField line, these are pretty much interchangeable, these terms. DPUs are important because they can act as a network card on its own, as well as a separate host alongside the servers they're connected to. And this is a particular interest to HPC researchers because this allows us more resources to utilize. Who doesn't want more resources with already a buttload of resources on the host, right? Furthermore, these are basically another accelerator that, alongside GPUs and FPGAs, is evolving super rapidly. So to get into this, SmartNICs are getting smarter, effectively, and at a rapid pace. 2021 saw the release of the NVIDIA BlueField 2 DPU with an 8-core ARM CPU, 16 gigs of RAM, and up to 200 gigabits per second of HDR InfiniBand. And plenty of literature that's been published in the past 2.5 years has shown how capable it is of offloading communication and computation from its host server. At the end of 2022 and throughout 2023, we are seeing and have seen the release of NVIDIA's BlueField 3 with nearly double the computing power of the BlueField 2. And I'll get into what I mean by nearly double in a minute. So this gives us 2 problem statements to deal with. How smart is this SmartNIC compared to its predecessor? And given our in-depth comparison of these 2, can we predict the trends of upcoming SmartNICs, such as AMD's Pensando DPU, which has recently been revealed, as well as those from, say, Marvell or potential other vendors such as Intel. So now, speaking of hardware characteristics, let's get into them. Most of these are found through the publicly available data sheets on NVIDIA's website. The only one that isn't is the clock speed for the BlueField 2, which was given to us courtesy of David Cho through a root-issued LSPCI output. So thank you, David. Really appreciate it. Starting with the BlueField 2, just to break them down bit by bit, we have the 8-core ARM Cortex A72 CPU running at 2.0 gigahertz. This features 32 kilobytes of D cache and 48 kilobytes of I cache in the L1 space, 1 megabyte of L2 cache, 6 megs of L3, 16 gigs of RAM, and this in particular is on one memory controller. This will be particularly important to us later on. This features DDR4 memory at 1600 megatransactions per second with up to 200 gigabits of InfiniBand, as we discussed previously. Its younger sibling, the BlueField 3, runs as follows. We have the ARM Cortex A78 CPU with 1.5x the clock speed and double the core count. We also feature up to double the cache space in the L1 region. So interestingly enough, half the L2 cache space, which becomes important later on, 16 megabytes of L3 cache, and 32 gigabytes of RAM across 2 memory controllers. Furthermore, what's really impressive is how we have a 3.5x improvement in our RAM clock speed with an evolution to DDR5. And then as mentioned before, a doubling of the interconnect speed, so going up to 400 gigabits per second of up to NDR InfiniBand here. So let's get up into our methodology and setup. Firstly, we use the Thor partition of the HPCAT cluster. And I'd like to thank the HPC AI Advisory Council for their allowing us to use their resources. This partition features 32 nodes of 32 core Intel CPUs, so 16 cores times 2 sockets, running at 2.6 gigahertz. So immediately with some foreshadowing, we note that the host server already has a clock speed lower than that of the BlueField 3, as well as a lower L1 cache space than a smaller L1 cache space rather, and a smaller L2 cache space, while still holding out on L3 cache thanks to some smarter Intel technology. Each node also features ConnectX-6 InfiniBand adapters and one BlueField 2 each, also running at 100 gigabit per second HDR InfiniBand. The memory here is listed particularly because of our initial experiments featuring single DPU or single node comparisons. Half of these nodes are also equipped with BlueField 3s running at 200 gigabits per second NDR InfiniBand. So to break down some methodology and terminologies for our experiment subsets, for our single DPU, multi-DPU, host/DPU, and DPU-aware MPI library experiments, we run our executions back-to-back 10 times and take the arithmetic mean of our runtime, latency, and bandwidth. For some terminology clarification, our single DPU experiments refer to items done within one DPU or compute node, and multi-DPU refers to communication between DPUs exclusively. More importantly, I wanted to explain that we mean DPUs of the same type. So BlueField 2s will only talk to BlueField 2s, BlueField 3s will only talk to BlueField 3s. We do not investigate the performance of multiple generations of DPUs here. DPU bench is a benchmark suite I'll explain in some later slides. And due to time constraints on Thor, we only run 4 back-to-back executions for our configurations and take the arithmetic mean of our offload efficiency, which we'll also explain in the same subsequent slides. So we get into our single DPU experiments. Our first one deals with memcopy. And in particular, we examine the latency of the memcopy operation found in C for a single process. No offloading is performed here, just to clarify again. And so given the increased cache sizes, clock speed, and core clock speed and memory speed on the BlueField 3, how does it compare to the BlueField 2 and host-based memory? We examine message sizes across the entire gamut of 64 bytes to 1 gigabyte to showcase behavior at all levels when spilling from L1 to L2 to L3 and into DRAM. We also include cold cache numbers in our final arithmetic mean, which doesn't really differ, or really doesn't destroy the trends that we see here. We see identical trends in those numbers as well. So firstly, memcopy, again, as some trivia, is one of the most highly used functions across HPC applications and regular applications, particularly those programmed in C and C++, among other spots. Generally, our BlueField 3 outpaces the BlueField 2 up to nearly 60%, as well as comparably more than the host server as well. CPU clock speed, memory speed, and cache sizes kind of take the cake here. One thing to note here is that we use a log-based scale for our middle range of messages, given that anything below 8 megabytes was particularly hard to see with a standard y-axis. Everything else kind of runs relatively fine here. The degradations where we see the host outpacing the BlueField 3 are in technically 3 spots. We see a near degradation or matching performance at 32 kilobytes, where we start seeing the L1 cache kind of take itself into effect. And then we see anything between 4 and 32 megabytes, technically even 1 and 32 megabytes here. And then anything less than 8 kilobytes is where the host kind of ultimately does better than the BlueField 3. Beyond that, the BlueField 3 and host both outpace the BlueField 2 by a wide margin, and we see that especially as we hit 1 gigabyte message sizes. For more multi-threaded approaches, we look at the stream benchmark. Stream as its own was designed in the early mid-90s to measure memory bandwidth from main memory, or DRAM these days. So again, this refers to the 256 gigs on host, 16 on BlueField 2, and 32 on BlueField 3. Given that the BlueField 2 only has 8 cores, we limit our experiments to 8 OpenMP threads to make as close of an apples-to-apples comparison as we can. 2 things we'd like to note here are that use of 16 threads on the BlueField 3 gives a marginal benefit beyond 8 threads, as the memory bandwidth is nearly fully saturated at this point. And to ensure consistent thread placement and affinity, We verify our performance with the use of assigning cores for the OMP places variable and the use of NUMA-CTL while providing a CPU list. Furthermore, for some completeness, we also use arrays of size 10 million and 100 million here. So looking at the 10 million element array results, we see already a similar trend to memcopy, except this time with applications to bandwidth and not latency, where at 8 OpenMP threads, we see a more than 5x improvement in bandwidth compared to the BlueField 2, and a near 3x improvement at 1 OpenMP thread compared to the BlueField 2. The host also outpaces the BlueField 3 by about 30%, as we see here, more or less, thanks to larger memory banks, larger L3 cache, and more memory controllers at 8 OpenMP threads, whereas the BlueField 3 still wins out against the host at 1, 2, and 4 values. Use of the 100 million element array saturates memory marginally more than using a 10 million element array, but we see similar trends compared to our previous slide. The use of multiple DPUs here involves what I mentioned prior, just DPU to DPU communication across DPUs of the same type. And here we make use of the OSU micro benchmark suite with an emphasis on point-to-point communication across the network. So in this case, we deal with latency, unidirectional bandwidth, and bidirectional bandwidth. First off, we look at latency, where starting with smaller messages, we see improvements even at 1, 2, and 4 bytes, for example, thanks to our memory and core clock speeds. And as the bandwidth starts getting saturated, we see up to a 1.78x improvement in latency compared with BlueField 3 to BlueField 3 communication compared to BlueField 2 based communication. Larger sizes, so anything 16 kilobytes and up, see a significant boost up to 2.34x improvement if measured like so, thanks to our cache sizes and 200 gigabit per second InfiniBand. Unidirectional bandwidth sees similar trends, so already a 45 to 50% improvement at smaller message sizes, a 1.65x improvement in bandwidth at 16K, and everything kind of tapers out at 128 kilobytes or even 256 kilobytes because of our bandwidth getting fully saturated pretty much here. So here we pretty much see the 200 gigabit per second NDR and 100 gigabit per second HDR InfiniBand as showcased in our larger messages. Looking at bidirectional bandwidth, smaller messages show a similar trend, whereas larger messages see an interesting phenomenon. Thanks to the architectural components like one memory controller, smaller caches, and a slower memory speed, we see a degradation at 4 megabytes that is not seen in the BlueField 3, which leads to a 1.73x improvement in memory bandwidth. Now we get into our naive host and DPU based experiments. So we examine the same experiments, but with naively placing one process on the host, one process on the DPU. And we make 3 important things known here. Firstly, we require the use of a multi-program, multi-data mode in a traditional MPI library. In this case, we use the MBAPH2 library featured from my lab at OSU. We also make the assumption that rank 0 is placed on the host, with rank 1 being placed on the DPU. And we also try to force the proper HCA, or host channel adapter, on our host nodes with the BlueField 2 and BlueField 3. So BlueField 3 has been plugged into MLX50, BlueField 2 plugged into MLX52. To change things up, we take a look at unidirectional bandwidth first. Smaller messages show similar trends to our inter-DPU experiments, where here we see up to a 2.11x improvement in bandwidth with host to BlueField 3 transfer. However, we only see 14% improvement at larger messages. So what happened here? Effectively, we've come up with the theory that because the BlueField DPUs are in separated host mode, they use their own HCA, while the host process unfortunately ends up using something different, even with our assignment, such as a 100 gigabit adapter or a network card. And this creates an imbalance that we ultimately don't get to see the maximum possible bandwidth that we had seen prior with inter-DPU experiments. A similar trend occurs with bidirectional bandwidth, both at small and larger messages. And even with our host to DPU based runs, we see the similar degradation that we had seen with our inter DPU runs for bidirectional bandwidth as well. With this degradation at 4 megabytes, while pretty much getting our actual maximum bandwidth of 200 gigabits per second here with the BlueField 3. Our host DPU latency features a 35% improvement at larger messages, with similar trends shown previously with smaller messages. And here, looking at the raw numbers, it's not obvious here, but we see a up to 3% benefit compared to inter DPU OSU latency, inter DPU results. Now we get into DPU bench. This is a DPU bench was a benchmark suite that I presented at PERC 2023. The proceedings should be available now, if I recall correctly. And the gist of DPU bench is, given a collective message size, scale, and number of worker processes placed on the DPU, how efficient can we offload said collective pattern to a given number of workers through naive staging and IB-verse primitives? We calculate offload efficiency here using the reference time of a pure host execution divided by the maximum of pure com and compute multiplied by 100. We replicate my paper's experiments on the BlueField 2 and BlueField 3, featuring 8 nodes and 8 ppn on the host, with additional processes requested as workers to be placed in the DPUs. So we look at 8 different worker values and 6 different message sizes. And so because of the amount of data points we have here, we show a subset of results for brevity's sake. So initially, we look at the offload of a linear broadcast through cyclic distribution of work. So what I mean by linear broadcast is, if we were to do this on the host, the root would iterate through its non-root compatriot, so to speak, and issue a send operation. In this case, through cyclic distribution, we perform a round-robin assignment of work to the worker processes through the use of RDMA reads and writes. On the BlueField 3, while we see a largely unchanged result set for 2, 4, and 6 workers per node, we see increased visibility of potential degradations due to work imbalance. So while, for example, we see a measurement of 98.6, 98.7 on the BlueField 2 for 2 workers per node at 4 megabytes, and see maybe 98.6, 98.5, we see potentially 97, 96 for the similar worker counts on the BlueField 3. The upside of this is that the extra memory controllers on the BlueField 3 give an improved 8 workers per node efficiency. So here we use 8 workers per node, which is 8 workers per BlueField 3 per node, and offload communication accordingly. Thanks to the increased memory controllers and clock speed and the fact that we have resources left over, we see this improvement on offload efficiency here. Similar trends are shown in gather across 2, 4, 6, and 8 workers per node. And then we get into what I called in the paper an enhanced all gather, where we tag buffers accordingly to prevent overwriting from multiple workers on multiple DPUs. The BlueField 2 results from our paper show expected trends in efficiency compared to 1 worker total, and we see even more enhanced trends on the BlueField 3. At the 6 worker case, one thing we noticed from the raw results, which was particularly interesting, was that our computation took a shorter time than communication, thanks to the increased clock speed of the BlueField 3s. And while we cap our offload efficiency at 100 here for readability, this actually gave us a value of over 100. So offloading a linear all gather, where just every process does a for I equals 1 to end, send or receive accordingly, we show how efficient this can be just through improved hardware metrics alone. At 2, 4, 6, and 8 workers per node, we see that the better numbers shown on the BlueField 2 get better, and the degradations that we saw at 6 workers per node get substantially worse. Unfortunately, it's not a trivial thing to have to profile the BlueField 3. The use of Linux's perf tool, for example, may not help here due to output either being taken from the wrong process if you specify output, or the fact that we have to take results from every process and search for the right one. To the best of my knowledge, no patch has been made available in the Poppy tool for the ARM Cortex A7-8. So the minute that becomes available, that will infinitely help us understand why these trends are what they are. It's particularly given that public patches are available for the Cortex A7 II or the BlueField 2's processor. Now we get into our kind of like the height of our experiments with the use of a DPU-aware MPI library. Courtesy of Xscale Solutions, we were able to obtain a license for their NVAPITch2 DPU software, a DPU-aware MPI library with optimized performance in MPI IL-12 and MPI IBCAS, and we focus on the former through use of the IL-12 OSU microbenchmark and a modified P3DFFT application. We compare sets of numbers from pure host, meaning no DPUs used, enhanced staging designs, and the use of the guest virtual machine ID or GVMI firmware. GVMI, for reference, exposes host memory regions to the DPU, which allows for more efficient offloading over staging designs. We effectively you end up reducing the number of RDMA operations used with GVMI, and you get massive improvements compared to staging. GVMI, as I'll mention time and time again, is architecture agnostic. So the use of a BlueField 2 versus BlueField 3 will have little effect based on our results for IL-12 and our P3FFT application. So for starters, BlueField 3, the use of staging on BlueField 3 in NVAPITch2 DPU already wins over staging on the BlueField 2 by up to 20%. And both mostly win over pure host up until we hit 128 kilobytes. Once we hit 256 kilobytes, we start seeing degradations with staging, and so we stop our results there. However, we see only at most a 10% benefit of the use of GVMI on the BlueField 2 compared to on the BlueField 3 compared to the use of GVMI on the BlueField 2. And again, this is thanks to the GVMI being an architecture agnostic firmware and tool. We see similar trends even with increased runtimes with 16 processes per node and 32 processes per node. So this just goes to show that while staging helps out immensely, GVMI even more so compared to pure host, compared to the BlueField 2, GVMI again will not have as much of a benefit here compared to what we might expect. Lastly, we look at an application level result with P3DFFT. We've worked with the developers to make a modified version that implements a non-blocking all-to-all as opposed to the default using blocking all-to-all. Furthermore, the P3DFFT's applications can take in a process mapping file, traditionally read as X cross Y in some grid, while here for simplicity, we interpret it as node count cross BPN count, given that we're using all the processes available on the BlueField DPUs. Here we use a 1920 cross 1920 cross 1920 mesh size, and then we show results at 8 and 16 nodes with 8, 16, and 32 ppn. So firstly, at 8 nodes, we note that the problem size is a little too large for 8 nodes 8 ppn, and so that's why we only see minor benefits in between staging and GVMI based results here, with the pure host being this paler green-blue line here. Once we scale up to 16 ppn, we start seeing the benefits of staging at this scale, showing a 34.5% improvement at 16 ppn and up to a bit over 44% improvement with the BlueField 3 using staging designs, with negligible differences between BlueField 2 and BlueField 3 using GVMI. Once we get into 16 nodes, 16 node scale, we actually start seeing these benefits get enhanced even more so. So here we see at least a 50% improvement between staging designs across all 3 scales, and then even more improved design, even more benefits when using GVMI. Even with BlueField 2's GVMI usage beating out the staging designs used on the BlueField 3. However, again, we see negligible difference with the use of GVMI on both SmartNICs. So Again, unfortunately, that is thanks to the use of architecture agnostic features, such as, again, GVMI. So now we get into our concluding thoughts, discussion, and future work. Effectively, the BlueField 3s can handle more substantial offloading capabilities and workloads than its predecessor. We see a 50% improvement at minimum in application level benefits with MPI-based staging designs, and even more so with GVMI-based designs compared to staging. We see a 5x improvement in memory bandwidth, such as what was seen in Stream, and similar benefit and similar trends found in just even mem copy latency. And we see largely improved offload efficiency in staging designs with DPU bench. Given the right system, a BlueField 3 will have stronger capabilities than its given host, which will allow a user to offload anything it sees fit. So computation, communication, different stages of deep learning training, for example, and more. For future work, we want to explore more applications and models, such as applications found in using OpenMP, MPI, PGAS, or a combination of these. Furthermore, we want to redesign our offloading approaches to utilize BF3s and their successors more effectively, and ideally generalize these to other SmartNICs. Again, what happens if we want to use AMD's Pensando DPU in an HPC setting, or Marvell's DPUs in an HPC setting? Again, I'd like to thank LANL and the US DOE for their funding and support. I'd like to thank the HPC AI Advisory Council for the use of their resources, and I'd like to thank the NSF for their funding and support as well. Thank you so much for your time, and I look forward to seeing all of your questions in the Hot Interconnect Slack. Have a great day. All right.
Thank you so much, Ben, for the awesome presentation. So I would encourage attendees to ask questions on the Slack, and the Ben will be able to answer them on the Slack directly. If we get any questions here right now, I will be able to ask it during the session also. So I do have a question for you, Ben. So you compare different kinds of applications. Do you have any insight on what type of applications can benefit most from NVIDIA's DPUs? And can we use DPUs to accelerate GPU applications? Maybe deep learning, distributed deep learning, or something like that?
Right. So on the application side, if you're using, say, a DPU-aware NPI library, then like no matter, ideally, so far at least with Advantage 2 DPU, anything that would use, say, a non-blocking alt or non-blocking bcast, and as other collectives get enhanced, then those would apply as well. More so, I think heavy communication intensive benchmarks would work, especially with the more advanced designs. Though if you're relying more so on computation than communication, then perhaps not as much. And if the BlueField 3 can handle it, then you might want to consider offloading computation alongside it. As for the second question, I know your research in the lab, for example, using the GPUs like 2 years ago. But as for the use of GPUs alongside DPUs, it's possible. It's just not, to the best of my knowledge, it just hasn't been explored too much in depth yet.
Okay.
Donglai from Xscale. Yes, so go on that. Sorry, Donglai from Xscale Solutions had that question asked towards him at the Mbappé user group meeting back actually yesterday. So like he pretty much gave the same answer. It's possible, just hasn't been explored yet.
Okay. And what type of communication primitives can be optimized on DPUs? You evaluated iGather and iAll2All I saw. Are there any other primitives that can be optimized?
And I think any and all collective operations could be to a point. And I know even Kaushik, or my lab mate Kaushik at IPDPS 2023, published a paper where he pretty much enhances also point-to-point communication. So if you have a design for anything point-to-point collective, or even one-sided operations, for example, then it can be offloaded effectively.
Okay, thank you so much for answering the questions. And in the interest of the time, I will let you go. And thank you for the great presentation.
Thank you. Thank you. Great seeing you again, Arpan.
Yes, nice to see you. Okay, so next we have Silver Sponsor Talk from Algo-Logic given by John Lockwood. So John Lockwood is the founder and the CEO of Algo-Logic Systems Incorporated. He's an expert in building FPGA accelerated applications and has created companies in the areas of low latency networking, internet security, and electronic commerce. He has worked at the National Center for Communication Supercomputing Application, NCSA, AT&T Bell Laboratories, IBM, and Science Applications International Corp, SAIC. So let me share my screen and share the talk.
Today, most developers write code. Today, most developers write.
1 second. Yes, I think you should be able to see my screen now.
Code to run in software. The software sequentially executes and runs on a microprocessor. But applications like trading need low latency. Likewise, real-time data systems need deterministic response times. By building systems that run in logic, we build systems that consistently outperform those that still run in software. That is Algo-Logic.
One of the key characteristics that the customers bring up as we begin our engagements is the strength and the credibility of the development team.
There's a thing we do called debugging, which is fixing bugs. That is nonlinear, right? So that's sort of a distributed graph. You're walking through things. You run into a problem that leads to other problems, and fix things in the order that you run into them. So it's like sort of helter-skelter. That's typically how we make progress.
So I guess the reason I like working here is that everybody is nice, and some projects have important real-world uses, like making devices that measure structural integrity of buildings.
At Algo-Logic, working to satisfy our customers is our goal. We use principles of ownership, leadership, respect for others, and strong work ethic. We drive results like quality, solutions, competitiveness, and success.
Okay, thank you so much for attending this paper session. Now we have the break for 30 minutes, sponsored by the Lenovo, and stay tuned. Rohit.
F1's the pinnacle of motorsport. It's the most thrilling motorsport there is out there.
It's all about energy, innovation, technology, excitement.
Formula One is the most data-rich sport anywhere on the planet. Through the use of Lenovo technology, we'd like to bring the fans much closer to the action and to the sport.
As a company, we're constantly pushing, we're constantly looking on how we can grow, how we can expand, how we can be better. Lenovo being our partner helps us to achieve that.
Lenovo is very much a one-stop shop for us, which is fantastic. We not only get amazing technology, but also access to some of the best techies and expertise to help us build solutions. We've got to make 1,000,001 moving pieces synchronized and all come together in perfect harmony, and Lenovo helps bring that together for us. The race day for us, you can feel the tension building throughout the day. You can feel it from the technical operations people, the teams themselves, out into the grandstands.
The partnership with Lenovo is helping us be more efficient and effective across our whole organisation. Formula One's always on the edge of innovation, with the cars, with the fans, with our products, with the data, with the video, with the audio. Broadcast is key to what we do.
Thank you very much, everyone. Wonderful car.
The broadcast team has to process multiple camera feeds. You're talking around 26 track cameras, plus special cameras, onboard cameras, 360s. And that can be quite challenging at times. So a Lenovo infrastructure is the backbone of that platform. From a purely hardware and technical perspective, they deliver and respond every time. We have to have kit that travels globally around the world, so sometimes we are shaking that kit with high vibrations, it's frozen, it's cooked on a tarmac, and then we ask for that kit to work every time when we turn up.
Lenovo technology is at the heart of our race operations, whether that's back in our server rooms, in our RTC and ETC, whether that's Motorola handset. It really is what enables us as a business to connect with absolutely everyone.
We produce around 500 terabytes of media each event.
That content comes off the car in real time to our facilities back in the UK to service our fans. Data like the G-force the driver's hitting around the corner, the steering angle, the brake, how much he's pushing the throttle.
Things like the driver's point of view, the helmet cam, those give people an absolutely new focus of Formula One you've never seen before. So just gives an incredible insight to the sport. At F1, we have goals, we have vision where we want to go, and Lenovo can help us achieve it, and even better, they can help push us even further. One of the great things about a partnership with Lenovo is that sustainability initiatives are right at the heart of what we want to do. We're utilising Lenovo's asset recovery service, which means that we know that our hardware is going to help charities, help communities, or is being sustainably recycled.
The technology choices we make have to integrate into 100% reliable and repeatable solutions.
F1 and Lenovo share a quest for perfection. They help us understand what the art of the possible is, and together we build that.